Hello, I'm Emmanuel Ansa, and this is the video presentation of my machine learning assignment. Upon loading the data sets, I discovered we had 225 rows and two columns. And upon plotting the data, we can see some nonlinear pattern in the data. And looking at our response variable, it is a continuous variable, so it's literally a regression task. And since it's a regression task, the best function space is just some a linear combination of our betas, and the best loss function to use in the case of a regression is just the mean square error. So there's the theoretical risk, which is the expectation of our loss function. This is the integral form of it, and the f star of x, which is the base learning machine, is our expectation of y given x. And this is the empirical risk function, which is 1 over n summation of our loss function plus this complexity term here, the lambda being our regularization and the c of f being our complexity measure. So this is the derivation of the OLS estimator. Because of time, these are design matrix, and we seek to minimize our RSS, which is the residual sum of squares. So we find the partial derivative with respect to beta, and you end up with this normal equation. And these are some properties of the OLS is unbiased, and the popular blue, which is best linear unbiased estimator. So I went on to do a V-fold cross validation. I did 5-fold, 10-fold, and 20-fold, and they all show that degree 10 is the optimal one, which is also shown here in this plot here. And I went on to fit the data with polynomial of degree 1, of degree 10, and of degree 18, which is the complex part. So this is it. You can see the optimal one with the red line. It fits the data perfectly, or let me say, I'm tempted to say perfect, but I'll go with that. And the simplest is just a horizontal line. And our complex one also fits the data well. So in performing our stochastic holdout to see our test errors, the box plot showed that the simple one had a very large test error compared to the optimal and the complex. But in this plot, I can boldly say that the optimal had a lower test error. This could be because the complex one tends to increase when the degree increase to a certain point. And in our ANOVA also confirmed that there is a significant difference in at least two of our models. Okay. And the next one is 95% confidence and prediction band. So in this prediction bands, we can see that the the model is able to predict the data. Let me say 99%. I'm 99% confident in this model ability to predict our response variable, and the confidence interval being very thin shows the precision of our model. And this is the mathematical expression of our confidence band, and this is the mathematical of our prediction band. Um, the distribution of our response variable, you can see we had 2,788 non-spam and 1,813 spam, which indicates that our data, the class is what we have class imbalance here, and this could affect our classification models as well. And the ROC curve here also indicates that LDA and QDA are almost likely the same. They all have 95%, 95%. And the lowest performing here was the naive Bayes classifier. And upon doing a stochastic holdout of the errors in our models, I found out that our LDA was performing the best. It had the least errors among all of them. So in conclusion, the LDA was the best fit model for our data. Thank you.